Hello, how's everyone doing today? In this video we're going to discuss control valves and how to design a control valve for a given control process where the valve is the final control element. The information discussed in this video is based on the textbook Chemical and Bioprocess Control, the 4th edition, by James Riggs and Nazmul Karim. In most chemical process control systems, the manipulated variable is a flow rate, so the final control element is a flow valve. The components of the valve, or the actuator system, include the valve body, the valve plug and stem, and the valve actuator. So if we can fill in a few points here, we have the valve body. Okay, that will determine the maximum flow that can go through the valve. The valve stem and plug, which goes into the body, so the movement of the valve and stem is going to allow flow through the valve body. And the valve actuator. So the valve actuator is what moves the valve stem up and down in the control valve. Typically also as part of an actuator system there will be an IP converter, and this will convert the current that comes from the controller to an air pressure that can move the valve actuator, move the valve stem up and down. Another important part is the instrument air system that provides air to the IP converter and air to the valve to open and close the valve as needed. Shown here is a cross-section of a globe valve, which is a typical valve used to control the flow in a given chemical process. So a control valve will have an inlet for the instrument air. It'll have a diaphragm for which the air pushes against. Okay, the air in the diaphragm will also push against the spring. So with changes in the air pressure causes either a compression of the spring or decreases in the air pressure, the spring will push against the air to move the valve stem. So the valve stem can move up and down based on the action of air pressure and spring. Now depending on how the valve is designed, it can be air to open, which an increase in air pressure will cause the valve to open, or it can be air to close, whereas an increase in air pressure will cause the valve to close. The selection of either of those mechanisms is based on the desired operation or the desired performance of the control valve in the system. We'll come back to that later. Okay, there are three main types of control valves. Quick opening is the first one, and this is primarily used for safety bypass, and it doesn't typically work to control systems. We'll discuss why that is in a few slides. Throughout the rest of this video, we're going to discuss the differences between equal percentage and linear valves. The first important point is that the size of the equal percentage, or the size of the linear valve, is going to determine the maximum flow that goes through the body, the valve body. So again, the primary thing that we need in terms of designing a control valve is we need a valve that's big enough to accommodate our maximum allowable flow, and that will be something that's fairly straightforward to determine. Okay, the most common way to express valve performance is using the term CV, which is the valve coefficient. Okay, so the definition, the CV is the relationship between the flow rate and the pressure drop across the valve, and it's based on the following relationship. So the flow is equal to K, which is a constant, times CV, times the square root of delta P over the density. Okay, and so in this equation, K is a unit conversion. So K is going to convert the units between the flow, CV, or the flow, the pressure, and the density. To make things easy, we can use a value of K equal to 1 if the CV is gallons per minute, delta P is PSI, and rho is specific gravity. Okay, so as long as we use these terms, and then finally if we have water or something close to water, SG equals 1, right, and we'll use that for many design type scenarios. Then this equation is going to simplify to FV equals CV times square root of delta P. All right, and so now here it's very easy to see that CV is the relationship between the flow rate and the square root of the pressure in the system. So importantly, US vendors are going to report the values for CV based on these types of units as well. So it's in your interest to be comfortable working with flow rates in gallons per minute and pressure drops in terms of PSI. For linear globe valves, CV versus percent open is pretty easy. It's going to be based on the valve size. And you can, based on the valve size, you can get CV max, which is the maximum valve coefficient when the valve is entirely open. For our class or for other purposes, you can typically use a CV max that you get from a table that may be given for equal percentage valves, and we'll get to that in a second. Okay, so for linear valves, if we want to know CV as a function of x, CV as a function of x is going to be equal to CV max, right? This might be given, times x over 100. So when x equals 0, the valve is entirely closed and CV is 0. There's no flow. When x is equal to 100, the valve is entirely open and the CV is equal to the maximum CV that can be delivered from the valve. Okay, well, to do a quick example here, if we have a 4-inch valve, and from the table in the textbook we can get a CV max equals 190, right? If the valve is 65% open, right, then we can get the valve coefficient CV equals 190 times 65 over 100, and this is equal to 123.5. All right, so essentially from here, this is for a linear valve. If we plot CV versus x, we get CV that goes from 0 to CV max when the valve is 100% open. Linear valves are used when the pressure drop across the system is fairly constant, and that means with flow. Right, so what that would mean is that the line losses are typically small, the pressure generated from, or whatever the driving force is for the flow, is fairly constant. So this could be something like a gravity-driven flow where you have a constant hydrostatic head above the control valve. For equal percentage valves, the CV versus percent open must be found in a table. In the textbook, table 2.1 is shown here for a variety of different body size valves going from 1 up to 4 inches. For linear, if we're doing linear valves, we can just go to 100% open. We can use this to get CV max for a linear valve of the same size. All right, so for equal percentage valves, to get CV as a function of x, we're going to have to use this table and potentially even linear interpolate between values on this table. Okay, so one of the main differences is for equal percentage valves, if we plot CV as a function of x, right? For linear valves, we said that the CV is linear with x from 0 to 100%. So for equal percentage valves, it's going to be a little bit different. Equal percentage valves will have more of an exponential shape associated with them. At low flows, the CV won't change much when the valve opens, whereas at high flows, the CV is going to change quite a bit when valves opens. And so the purpose of this is to get fairly constant changes in flow rate for changes in valve position. The next thing we want to discuss is the inherent valve characteristics. And this is the performance of a valve if the delta P is constant, so there's no change in pressure across the valve. Okay, if we look at how the inherent valve characteristics work for the 3 different types of valves, we'll see for quick opening. For quick opening valves, what we can see is that immediately the valve opens up and the flow is almost entirely established, or it's established very quickly. In many cases, depending on the design of a quick opening valve, it can even be greater than the performance shown here. Okay, this next curve is pretty easy to determine what it is. This is a linear valve where the performance, or where the slope of the fraction of the full flow, which is related to CV, is constant with stem position. Because remember, from our relationship, FV equals CV times delta P, if this term is constant, then your flow is proportional to your CV. Okay, for equals percentage valves, it's shown here. I want to point out that this point right here should probably go or does go through 0 rather than how it's shown on here, so I'll draw that on here a little bit better. Okay, so for for an equal percentage valve, the CV changes only a little bit initially at low valve positions and changes by quite a bit at high valve positions. So again, CV, or the flow is proportional to CV, so we can think about this as CV in addition to a fraction of the full flow. Okay, and this is an example of the inherent valve characteristics for each one. So what you can see here is that if you have a system that has a fairly constant pressure drop, your best valve for getting the control over the entire range of flow is to use the linear valve. Because for your linear valve, what you can see is you always have a constant change in flow as you change your valve position. So let's consider a case where we have a constant delta P. And a constant delta P might come from a system where you have gravity-driven flow. So here's an example of a storage tank. That has a fairly constant liquid level. It's always about 30 feet above the valve. So the pressure generated by this storage tank is related to rho GH. Right, so this, if the height's constant, this should give us a constant driving force, or constant pressure driving force across this valve. The also important assumption to consider here are that the line losses are low, or small, for the system. Right, so if the line losses are small, and the pressure generated by the pressure of based on the height of the fluid is constant, we would expect to have a relatively constant pressure drop across the valve. And if this is the case, like we mentioned, a linear valve is probably best. So let's see how that goes. So the first thing we want to do is to set up a plot of the pressure drop versus flow rate for a variety of components in the system. So here on the y-axis we have pressure change, on the x-axis we have flow rate. So in this figure we're going to plot a couple different things. First we're going to plot the pressure, and so this is the pressure of the hydrostatic head, and so this right here, it's based on the height of the fluid. Okay, the other thing we need to calculate in the system is the line losses. We said the line losses were low, but in order to get an accurate measurement of an accurate description of the valve performance, we need to determine what the line losses are. Line losses are all pressure losses in the system except the valve. That could be from the permanent losses in the orifice plate meter, skin friction of the flow in the pipe, elbows, etc. Okay, so if we take the difference, we can get delta P of the valve. And the delta P of the valve is the difference between the delta P of the hydrostatic head and the delta P of the line losses. Once we calculate the delta P through the valve, we can go back to our equation from previous where we have flow equals CV times square root of delta P over SG. And again, as long as we're in GPM and PSI, this will work. So already we have data for the flow rate, and we have data for the pressure drop across the valve, and we should know the specific gravity based on the fluid. Based on all that, we can now calculate the CV versus flow rate. And based on the performance of the valve, or based on the flow performance of the type of valve, So based on size and the type of valve, we can generate a plot that shows flow versus X. Right, and so that's what we want to do. On this slide, we're now looking at the installed characteristics of the valve, or installed valve characteristics. And this is going to be for 4-inch linear and 4-inch equal percentage valves. So again, the way that we constructed this plot was this installed flow rate shown here. These are specified flow rates over which we want the system to operate. So these, we can consider these as in essentially given. Right? So given the flow rates, we calculated the pressure generated based on the hydrostatic head. We calculated the pressure losses associated with the lines, and we got the delta P through the valve. Based on the delta P through the valve, we were able to calculate CV using FV equals K, actually K equals 1, delta P over SG. And then using the valve, so for the valve, CV equals X over 100 times CV max for linear, or CV equals values for the table for equal percentage. All right, so using those values, we were able to calculate X, which is now given down here on the bottom. So X is the percent open. So these values were calculated for the given flow rates, which had corresponding pressure losses, etc. Okay, so if we now using this data for the installed flow rate plotted versus stem position, we can identify which valve would work best for this given system. If we look at the linear valve, what we see is over a range of about 10% open up to about 85, maybe 90% open, we see that the valve performance is fairly linear with respect to the percent open. Whereas the equal percentage valve, what we see is initially the flow rate doesn't change very much as we open the valve, and then it changes quite a bit. So really with the equal percentage, we effectively only have control of the flow over a very small range. So based on these properties, what we can see is that the linear valve would be much more suitable for this application than an equal percentage flow valve. Okay, let's switch gears now and look at a more common application, which is a flow that's driven by a pump. So the difference here is that when flow is driven by a pump, the pressure generated by the pump is a strong function of the flow rate required. So as you increase the flow rate required by the pump, the pressure generated by the pump is going to decrease. This change in pressure associated with the flow rate is going to have a big impact in how the valve performs, or how the flow responds to changes in valve positions for the different types of valves. Right, so the example that we'll show is here, and again, the only thing that's important is that, again, we have a pump that's used to drive the flow. So in this case, we're pumping the liquid flow from the accumulator back into the top of a distillation column, perhaps. All right, so just like last time, we have to first start by generating a plot of pressure drop versus flow rate. Okay, and again, we're going to do that. We have pressure on the y-axis as a function of flow rates. And again, this is just the flow rate, this is just a range of flow rates that we might want to investigate for the particular application. Okay, so the first delta P that we have is going to come from the pump. Okay, so in order to determine the delta P from the pump, we need to use pump curves, and the pump curves will typically be found in literature or supplied by the manufacturer of the pump. So the pump head, this is data that may be supplied by the manufacturer, so we have to find this somewhere. Okay, the next thing we need to look at, just like in the previous case, are the delta P associated with the line losses. The delta P associated with the line losses, this can be things like skin friction. We can have elbows. We can have orifice plate. And this is something that's used to measure the flow. And again, when we consider the pressure drop from the orifice plate, we only have to consider the permanent pressure drop and not the pressure drop that's immediately across the orifice plate that's used to determine the flow rate. Other things that can affect the delta P losses in the system are if you have a change in pressure from your source, from your source to the destination. If you have a height change, if the fluid undergoes a change in height, we have to consider those pressures as well. And we typically just group all of those terms into delta P of the line losses. So any pressure term from the mechanical energy balance that is not considered, or that is not the valve. Right, and so finally we can just subtract the pressure generated from the pump with the delta P of the line losses, and this gives us our delta P associated with the valve. And you can see here that because the pressure generated by the pump decreases with increasing flow rate, we have a much stronger change in pressure across the valve as a function of flow rate in this range. One thing you'll notice is that the valve delta P will eventually go to 0. Now it can't go exactly to 0. Once the line losses are equal to the pressure generated by the pump, you just can't get any more flow rate through the system. Okay, so next thing we want to do is, again, follow the same process that we used last time. Here we have a valve delta P, and down here we have flow rate. And again, good, we have things in our proper units. So using this, we can use our equation FV equals CV, square root of delta P over SG. And this will allow us to calculate CV over this whole range of flow rates. Using the calculation of CV, again, we can, based on the valve, we can get X. Right? For the linear, it's straightforward. For the equal percentage, we'll use the table. Now we're back to the plot of the installed valve characteristics for the pump-driven flow system. Again, we have the flow rates, and these are given. These would be flow rates where we would target operating our system. If we wanted a bigger flow rate range, we would have to vary the range, etc. The stem position, this is our X. We calculate the stem position from the stem position comes from CV, which is calculated from the previous plot using the relationship between flow and pressure drop across the valve. Okay, if we calculate that now for the pump-driven flow system, we can see two different characteristics. For the linear valve, we see installed characteristics that look as shown here. And then for the equal percentage valve, we see characteristics shown here. One of the things to point out is that neither of these valves work particularly well above 80% open. So typically one of the heuristic rules in designing a valve is valves are never designed to work when open greater than 80–85% because there's no control really over the flow when a valve is nearly fully open. Also, valves typically aren't designed to operate below about 15%. When valves are below about 15% or so, the valve stem will make contact with the valve seat and eventually wear and erode the body of the valve and cause it to need to be replaced at a higher rate. Okay, so what do we notice for these two conditions? What we can see here now, the equal percentage valve, it has a little bit of a change in slope to it, but we see a fairly constant change in flow rate with respect to stem position, whereas for the linear valve, at low positions, from about 10% up to about 40%, we have the most change, but for anything above 40 to 80% or 30 to 80%, here there's no effect on the flow. So for pump-driven flow systems, where there is a large change in pressure drop across the valve, equal percentage valves typically gives you a better performance than a linear control valve. Another way we can look at these valve characteristics is shown here, where we're looking at now the slope. So this is the derivative of the installed characteristics. So how does the flow change in response to changes in the stem position as a function of stem position? Ideally, you want your valve, your flow rate to change to be constant with respect to changes, or to be constant with respect to stem position, so that your controller can give the same performance at high flow rates versus at low flow rates. What we see here is if we look at the linear valve, the slope, initially there is a very high slope, right? So I'm going to cut this off about right here, and let's look at this range. Right, so initially there is a significant change in how the flow rate responds to changes in stem position, and what this means is that the ability to control the system is going to change quite a bit when you go from here to here. Right, once you get to 40% up to 80% open, now you're fairly constant. There's not a significant change in performance as you change stem position. Okay, if we compare that with equal percentage valves, let me draw this a little bit better. Equal percentage, what we can see is initially we vary between about 2 and 4, right? So our gain, so the change in flow with respect to change in stem position, is going to be fairly constant over the entire range of flow. Now again, this isn't necessarily ideal, but in terms of if we look at the performance over the entire range, you can see that the gain varies really between about 2 and 4, whereas the gain on the linear valve changes between 7 and much less than 1 for the linear valve. Ideally, we'll want a valve that operates with a fairly constant slope, but that may or may not be achievable because you're not going to design a new specific valve for every different process. Let's spend a couple minutes on control valve sizing. So when we size a control valve, we want to typically start with the average flow rate that we expect to go through the flow valve, and we want that average flow rate to be somewhere operated with a valve position somewhere between 50 and 70% open, and that's just a general rule of thumb. Over all of we want to make sure that the valve is open at least 15% and no more than about 80% over the entire range of flow required. So at the minimum flow rate, the valve should be opened at least 15%, and at the maximum flow rate, the valve should be open no more than 85%. So typically we can use these two guidelines to identify a valve that works best for a given process. Now if none of these can work, there are other options that we can do. Later on we'll talk about split flow control, where we have a small valve and a large valve that work together. And also if you identify more valves, multiple valves that can work for a given system, you might have to use your judgment. So if you care about minimizing the cost, you might go with a smaller valve. If you want to allow for an increased capacity later, you might use a slightly larger valve. Typically the smaller valves are going to be a little bit better because they'll give you more precise changes in flow with changes in valve position, because you're using more of the range of the valve to achieve the target ranges of flow within your given process. Okay, I'm going to come back to this slide so that we can go through a quick example on selecting a control valve. So I don't have a lot of room on this slide, but I'm going to write some information. So we want to select a control valve that gives us a maximum flow of 180 gallons per minute, a minimum flow of 30 gallons per minute. It's a pump-driven process, so we're going to use a pump-driven process, right? So this pump-driven process pretty much tells us that we want to have equal percentage valve. Right, so we're going to use this plot for the performance of the system. So this curve right here is going to tell us this is our actual pump that we're going to use in the process. Someone else did the dirty work and calculated these line losses for us, and so these are going to be the line losses that we'll use. So we need to have a valve. We need to select a valve that's going to give us this range of delta P across the valve over a flow rate range of about 30 up to 180. Okay, so for the equal percentage valve, we'll use table 2.1, and I can go back to that valve table in just a second. Okay, so first we want to know what is our delta P across the valve at the minimum and maximum flow rate. So at the minimum flow rate, our delta P, if I read this off the plot, maybe that's between about 19 and 20, so I'll say 19.5 at our minimum. At our maximum flow rate, we're somewhere around here. Okay, if I read this, if I draw this over here, maybe this is about 6.5 psi. Now ultimately what I would want to do is not necessarily read these values off the chart, but use the tabulated data so I get a better idea about what that actual pressure drop across the valve is. Okay, so now that I know these pressure drops, I need to calculate the CV min. Right, so the CV min, this is going to be equal to the flow rate, which is 30 gallons per minute, over square root of 19.5. Right, in this case, actually, I didn't say earlier, but we're going to assume we have water as our fluid. Okay, so I just rearranged our equation that relates flow, CV, and delta P. And we can calculate a CV min of, this would be 6.8. And again, we can also calculate CV at the max flow. I'm going to write CV max F, not to be confused with the maximum CV of the valve. All right, so this is going to be 180 divided by square root of 6.5. And if we run those numbers through the calculator, which I already did, this is 70.6. So I need a flow valve that gives me 19.5 to 17.6 over this range of flow. So let me go back now to my table. So again, I know my CV min. I'll just write that on here, 6.8 to 70.6. Okay, so now as I decide my flow valves, I'm going to just start by looking at the maximum. I know I need 70.6 as my maximum CV, so I can't use this valve, I can't use this valve, and I can't use this valve. Right, so there you go, now I have two choices. My minimum CV is 6.8. Right, and we want to make sure, again, we want to make sure our valve is open at least 15%. If I look at, if I look here, what we can see is that for a 3-inch valve, 6.8 is going to be somewhere between these two. And for a 4-inch valve, the CV is going to be somewhere probably a little bit closer to 10. So this probably corresponds with, you know, just rough idea, looking at interpolating by eye. This is probably going to be less than 15% for that 4-inch flow valve, right? But also one of the things I consider is the CV at my maximum flow rate is going to be between here, 60 and 70%. Whereas the CV max for the 3-inch valve is going to be up here. So the 3-inch valve is going to give me a little bit wider range of control